Ladies and gentlemen, to begin our workshop, we would like to invite all participants to listen to the Indonesian National Anthem, Indonesia Raya. We kindly invite everyone to listen respectfully during the anthem. Assalamualaikum warahmatullahi wabarakatuh. Ohayo gozaimasu minasan. It's a great honor and pleasure to welcome you to the collaborative research workshop on understanding tropical precipitation system through the integrated radar and satellite of precipitation. And this workshop marked a valuable joint research collaboration between Research Center for Climate and Atmosphere BRIN and Center for Orbital and Suborbital Observation ISEE Nagoya University. This workshop is being held today, Tuesday, 21st March 2026, virtually through the Zoom meeting application. Ladies and gentlemen, please allow me to introduce myself. My name is Kristanti Permata VDRC, and I'm honored to serve as the host of today's workshop. This morning, we are privileged to have our distinguished guest, the Honorable Dr. Albertus Sulaiman, the head of Research Center for Climate and Atmosphere BRIN. Our speaker, Professor Nobuhiro Takashi, Director of Research Center for Orbital and Suborbital ISEE, Ms. Sofia Lestari, PhD from ISEE, and also Dr. Wendy Harjupa, Mrs. Rahmawati Syahdiza, and Mrs. Anis Purwaningsih from BRIN. And our moderator, Dr. Ardi Adari Arbain from Research Center for Climate and Atmosphere, and all research group coordinator, participants, and guests of today's workshop. We are truly delighted to have all of you here today, and we hope that this workshop will foster meaningful discussion, insightful knowledge exchange, and stronger collaboration between our institutions. And before we start our agenda, I would like to inform all participants regarding the webinar's rules of conduct. Please mute your microphone when the speaker is speaking and use the raise hand feature or chat box to ask questions. Participants are kindly requested to rename themselves using the format your name underscore your institution. Participants are kindly invited to use virtual background that has been provided. And ladies and gentlemen, we are now in the opening ceremony session. Without any further ado, it's my honor to invite Dr. Alberto Sulaiman, the head of Research Center for Climate and Atmosphere BRIN, to deliver his opening remarks. To Pak Alberto Sulaiman, the floor is yours.
Okay, thank you very much. You can hear me? Okay, clear? Suara? Halo?
Yes, Pak, clear.
Okay, okay. Thank you very much. The first, thank you, welcome, Nobuhiro Takahashi Sensei for coming in our seminar related to the importance of development of radar and satellite technology for observation and understanding about precipitation and also rainfall in Indonesian maritime continent. For me is very remarkable, but in 1960, the Matsuno Sensei from Todai, he play with toys, mathematical analysis, shallow water in the equatorial beta plane and something, and he with his mathematics he insight to predict the many behavior of atmospheric wave and something in the Indonesian maritime continent. And then I think in early 1990, maybe the pioneer by Fakuo and Yamanaka Sensei, Fakuo Sensei, and Susumu Kasto Sensei, they established the first measurement in Indonesian maritime continent using many instruments, including equatorial radar, SODAR, LIDAR, and many things. So amazingly, the phenomena that predict by Matsuno Sensei only with mathematics, it can be observed now. I think it's very remarkable achievement. So from the Yamanaka Sensei investigation, more than maybe 40 years in Indonesia, I think he loved Indonesia more than Indonesian people. And he found that the energy dominant in climate or weather system in Indonesia is diurnal variation. So one of them in the last of his life, he worked with us and Osaki Sensei to investigate related the diurnal variation and related to the wetland or peatland. So our work can be read in our paper in scientific report in 223 related how the importance of when the wetland contribute to diurnal valuation and diurnal circulation related to the atmospheric dynamic in Indonesian maritime continent. So I also work with Mariko Ogawa from Kyoto University to establish more quantitative the effect of wetland into the diurnal variation. The paper still in review. So with the development of radar and satellite more precise, I think our understanding about the precipitation in Indonesian maritime continent will be increased. So for example, now we can see about the phenomena is called atmospheric river. Maybe in the next we can see in EMC the phenomena related to the maybe atmospheric waterfall or apa itu air mancur. Because EMC is the source of precipitation or water vapor that contribute to global climate. I think this is very important seminar, and I hope in the future we make more seminar more, and I hope we can more collaboration, especially the collaboration between Indonesia and Japanese scientists to increase our understanding about the equatorial dynamic Terima kasih Bapak Ibu semua, thank you very much. And berhubung saya di lapangan, kemungkinan tidak ada sinyal, nanti mohon Pak Trismidianto untuk memberikan catatan penutup ya di seminar ini. Terima kasih, thank you very much, and enjoy your seminar.
Okay, we would like to express our gratitude to Dr. Albertus Sulaiman for his opening remarks. Ladies and gentlemen, we will have a photo group session. Please activate your camera and video function, and we invite our documentation team to assist in taking a picture.
Okay, audience, please open your cameras. There are 2 slides. Slide 1, photo in 3, 2, 1. Oh. Slide 2, photo in 3, 2, 1. Oh. Okay, thank you.
Thank you, Mr. Mukhtar. Ladies and gentlemen, it gives me great pleasure to introduce our speaker, Professor Nobuhiro Takashi, Director of Research Center for Orbital and Suborbital Observation, ISEE, and Mrs. Sophia Lestari, PhD from ISEE, and also Dr. Wendy Harjupa, Mr. Rahmawati Shahridiza, and Dr. Anis Purwaningsih from BRIN. And in this session will be moderated by Dr. Ardi Adari Arbain. But before that, please allow me to read his brief biography. Dr. Ardi Adari Arbain is a researcher at Research Center for Climate and Atmosphere BRIN. He obtained his bachelor degree in meteorology from Bandung Institute of Technology, and he earned his master degree in electrical engineering from University of Indonesia, and doctoral degree in environmental science from Toda University. To Mr. Adi, you may take the floor.
Thank you very much. Good morning, distinguished college and participant. Welcome to this collaborative research workshop focusing on understanding tropical precipitation systems through integrated radar and satellite observations. So as we know, the tropical precipitation systems play a crucial role in regional climate variability, hydrological process, and extreme weather events. However, their complex structure and physical interactions remain a significant scientific challenge. So I think this workshop will provide an excellent platform to explore how the integrated radar and satellite observations can enhance our understanding and improve observational and modeling capabilities. So it is my pleasure to moderate this session, and I am delighted to introduce our first speaker. I think we can just go through the talk because our Master of Ceremony already introduced Professor Takashi earlier. So Professor Takashi, you have 30 minutes of talk, and we also have 10 minutes for question and answers. So I would like to give the time for Professor Takashi. Sensei, the time is yours.
Thank you very much. I was not allowed to share my screen, so please give me a permission to share my screen. Yeah, right now I cannot share my screen.
Sensei, you can start sharing your.
No, sorry.
Oh, really?
I need to,
He should
share
be
my
a co-host.
screen
Okay.
to
Now,
the
The
Zoom. So the
settings
please.
change. Pak Ardi, please make Sensei to be a
now try again.
co-host or.
Okay, now it's okay. Yeah.
Yeah, okay.
So, let me. Can you see my screen?
Yes,
Is
we
it
can see it.
okay? Okay.
Yes.
All
Okay,
right.
perfect.
Thank you very much. Maybe I should like anyway. Okay, thank you very much. And actually, this is a kind of fast workshop since BRIN and ISEE, signed the corporate research agreement. So, and anyway, so I'm Nobu Takashi again, and I'm a professor with ISEE, Nagoya University, and also I'm a GPM project scientist. Today I'd like to briefly explain about the GPM mission and ASCII mission, and mainly GPM case. We have already more than 12 years of data, so I'd like to explain about more like a climatological information about GPM and also including the TRIM satellite information. And also, 2 years ago, JAXA and ESA launched the ASCII satellite. This is a satellite equips cloud profiling radar. It enabled to measure the Doppler velocity to the nadir direction. So I'd like to show the several case studies using ASCII satellite. And so let me start with the current status or situation of the spaceborne cloud and precipitation radar missions. Hopefully, you know that TRIM satellite. It was launched in 1997. This is the world's first spaceborne radar to measure the precipitation, and followed by the GPM DPR. It was launched in 2014, so it's now about 12 years of the observation by GPM. And combining with the TRIM and the GPM, we have almost more than 25 years of data. Then on the cloud observation satellite, it was first launched by the JPL, NASA JPL. They developed a CloudSat and launched 2006. And then actually ESA and JAXA launched ASCII satellite 2024. Actually, unfortunately, there's no overlapping period. This figure shows that it seems like overlapping, but in reality, there's no overlapping period. But these two satellites aim to measure the cloud, more like a cloud, not a precipitation. And also, there's some trend to develop a very, very small satellite like a CubeSat. So JPL also developed and launched RayCube satellite. This is a 3U CubeSat in 2018, and this technology was used for the next INCAS mission. Actually, this INCAS mission tried to measure the precipitation by the tandem and developing processes of the cloud by the tandem satellite. Actually, INCAS equips 3 satellites, and each of the satellites has a K-band, very narrow source radars. And also, this technology was used for the private US company in Tomorrow.io, and they have already launched a small satellite in 2023. And talking about China, actually they have launched dual frequency radar like a GPM DPR, and actually it's really similar to the GPM DPR satellite. And they are planning to launch next one maybe this year or next year. And coming back to the GPM DPR radar, we are now start developing a new satellite. It is called PMM, Precision Measuring Mission, and in this mission, we have also Doppler measurement systems. Then, I'd like to summarize the trends in precision observation missions, talking about radar technology. Before the PMM or Earth here, it was a conventional radar. We can get Z radar reflectivity only, but it's going to be a Doppler radar. So radar reflectivity and Doppler velocity are available. And also, as I mentioned in the INCAS mission, people are thinking about delta T observation. I mean the tandem satellite to observe the developing processes of the convective clouds. And science, talking about science, we have been long-term researching about using Z profile and rain map like a GIS map and to analyze extreme rainfall or diurnal cycles and so on. But in addition to these studies, maybe right now the research is going to be combined dynamics and cloud physics. More like dynamics process is important. And so then we can get evolution processes of precision systems. And hopefully we can get aerosol to cloud to precipitation interaction. And talking about space agencies or development status, it was a kind of agency-driven development, like JAXA developed a satellite or NASA developed a satellite, but it's going to be a agency private sector collaborative development. So more like we invite private sector to develop satellites. So let me move on to the GPM. It is global precision measurement. So this is a combined radar and multi-satellite radiometer observation for frequent global precipitation estimation by JAXA, NASA, and international partners. So main satellite is called core observatory that equips dual frequency radar and radiometer. And there are so many radiometer satellites from the international partners. And in GPM era, we achieved better global precision estimation, and also we did characterization of precipitation system like a convective stratigraph or a solid precipitation. And also we assessed the global distribution of extreme precipitation events. And also GPM data are utilized for the application like application for numerical weather forecasting and development of global precipitation map like GIS map. We have hourly 0.1 degree precipitation map like this. And actually GIS map data is applied for the flood forecasting. And let me talk about a little bit about sensors. So this is an overview of the GPM core observatory, and we have big two boxes, right? Bigger one is a K-band radar, and the smaller one is a K-band radar. And also we have GPM microwave imager. It is called GMI. So, and this is just maybe the before lunch in NASA, they are testing the GPM core observatory. And so satellite altitude was 407 kilometers until November 2023. Then we raised the satellite orbit to 442 kilometers to expand the mission life to overlap to the next mission. It is called PMM. And in this case, we set the inclination angle was 65 degrees. So that means covering the tropics and mid-latitude regions. And so major products from GPM DPR level 2. Right now, actually, several weeks ago, we just released version 08, but I'd like to mention explain about version 7. So you can get the PlayStation profile like a dual frequency and single frequency PlayStation profile and surface PlayStation rate and drop size distribution parameters like mass weighted diameter and number concentrations and convective statistical classification and path integrated attenuation. It is called PIA. This is a total range attenuation. And also there are several large solid PlayStation flag, like flag hail, flag gravel hail, or flag heavy ice precipitation. And also there is a multiple scattering index. It is called MS index, and it can be a proxy of hail existence. So, and actually data are freely available from JAXA G-Portal site. Yeah, you can use this barcode to the barcode, and this is just one example of the GPM DPR observation back to the 2016, and maybe this is a good example how the GPM DPR observes. And actually, we have only 250 kilometers swath width, so we cannot get the whole structure of the typhoon system. Maybe only half of the typhoon, but even though along this line we can get the radar reflectivity factor and median diameter, mass weighted diameter information like this. Actually, this tall cloud is echo is a eyeball cloud like this, and we also get such kind of three-dimensional information structure from GPM DPR. And yeah, actually, if you visit JAXA EORC site, you can get 3D rainfall watch site, and you can get various kind of precipitation event. And actually, JAXA has already developed a kind of automatic acquisition system for the typical precipitation events. So you can easy to find good cases for over the maritime continent or other places, and you can easy to see those three-dimensional structures like this. So I'd like to move on to the move on to the more like a climatological data set actually accumulated from the dual frequency precipitation radar since launch of GPM. So this is an example of the unconditional rainfall by convective precipitation, by stratiform precipitation, and overall precipitation. And right-hand side panel shows the conditional rain rate of the convective stratiform and all type. So probably you understand unconditional precipitation rain rate is defined like this. So total rainfall amount was divided by the observation count, not the rain count. And the conditional rain rate is total rainfall amount is divided by the rain count. So so conditional rain rate shows a kind of potential of each precipitation system. So looking at conditional rain rate, convective clouds has a very, very high potential of the precipitation, the precipitation intensity, especially over land. And the stratiform is a moderate precipitation potential, and there's no clear land and ocean contrast. And looking at unconditional rainfall, it is convective precipitation unconditional rain rate is concentrated over the tropical region, including Maritime continent and ITCZ like this. But for the stratiform precipitation, actually mid-latitude region like Japan or east coast of the United States, we have so many stratiform precipitation associated with extratropical cyclones like this. So actually, this is an overall view of the precipitation amount or of the a kind of climatological precipitation amount of globe. And I'd like to show various kind of similar map. In this case, mass-weighted diameters, less 3 panels, and normalized intercept parameter. It is of the drop side distribution for the right-hand side panel. So actually divided into the convective stratiform and all types. So looking at mass-weighted median diameter, actually overrun, there is larger raindrops are dominated, and even over the Maritime continent. So it is clear contrast between the land and ocean. And at the same time, the NW is opposite tendency. So the smaller number concentration, smaller and high number concentration appear over ocean like this. And for the stratiform precipitation, actually there is no significant contrast between the land and the ocean. So it is reflected to the total systems like this. And next one will be actually we have 3-dimensional structure by using the radar, so we can get something like this storm top height like this, convective cloud storm top height, and stratiform cloud storm top height, and total one. And in this case, actually, convective cloud includes the shallow convection. So, looking at Maritime continent, average storm top height is lower than the average storm top height of stratiform cloud. Yeah, this is just because of we counting the shallow convective cloud. But looking at land region, Africa or South American continents, there are high precipitation system appears in the convective cloud. And also we can get information like bright band with bright band means a kind of thickness of the melting layer thickness, and it is generally thicker in tropics. Maybe you can easy to imagine what is the difference between the tropic region and the high latitude region. And also this is a different information of the large solid precipitation distribution. And this is only the 3 months data of convective JJA 2019 and comparing the DJF 2019. And we are comparing the MS index. This is a multi-scattering index. This is a proximal existence of hail. And we also have a granular high hail. And this is simply granular and hail existence. And also we have heavy ice precipitation. This is a proxy of the large ice precipitation. So that includes a hail, granular, and probably large snowflakes. So generally, these kinds of information are similar each other, but looking at heavy ice precipitation over the southern mid-latitude Southern Ocean, there are so many heavy ice precipitation existed. Probably it can be as large snowflakes, but we need more investigation. And comparing the MS index and flag gravel hail is actually pattern itself is quite similar, but occurrence is quite different. So maybe MS index is only detecting severe hail events, probably, yeah, something like that. And also, this is actually, I didn't have enough time to calculate 25 years of precipitation since the TRIM satellite, but this is only 23, or probably 25. I don't remember but maybe 20, well, probably 25 years of data. And looking, we are comparing the single frequency rainfall estimation over land, over ocean, and all type of precipitation. And both we are comparing unconditional rain rate and conditional rain rate. Comparing these two, actually, we don't see clear or significant trend in global precipitation. Actually, we are averaging over 35° south to 35° north. So in this region, we don't have clear trend. No, we are someone expecting the increasing trend of precipitation by the global warming, but right now we don't have that kind of trend. And it actually, I just referred Kato et al. 2025. They are comparing the net radiation information. That means the long wave, outgoing long wave, and outgoing short wave budget. And also in their study, they are using the GPCP data, and they also mentioned about the near neutral trend in precipitation. And in their, from their study, they concluded that it can be explained by the increased shortwave heating associated with rising water vapor. So increasing the water vapor increase the shortwave radiation, shortwave heating. That means absorption from the solar energy. And also at the same time, long wave cooling. So the infrared cooling, radiation cooling is, activated. So that make it canceled out. But in near future, that can be, cannot be balanced. So that maybe we have to monitor more, longer term of the precipitation. And in their case, they are comparing the GPCP, that's a geostationary infrared observation based estimation, but our radar estimation is also similar result. And I just show the example of the comparison of various products of global precipitation map comparing with radar information. So GPCP is a geostationary IR-based algorithm, and they say they are considering a climatology. And there's a GSMAP and IMARCH. These are the microwave radiometer information with GeoIR-based algorithm. So combination of the microwave radiometer and the IR data. So generally GPCP and IMARCH, actually GPCP algorithm developer and IMARCH algorithm developer is a so many common people are committed both to products, so that those two products are quite similar each other. And on the other hand, GSMAP a little bit smaller rainfall amount comparing with GPCP and IMARCH. And but close to the radar observation, like KUPR, like this, ocean and land, and if we confine only the 35 south to 35 north, that kind of difference still exists. But maybe GSMAP and radar information estimation will be increased a little bit more. Yeah, but maybe there is still gap among the product of the precision map. And also, I did several trend analysis like this. This is a precision trend. And for example, actually I'm using only KU band because I'm combining both trim and GPM. So occurrence trend and conditional rain rate and unconditional rain rate in trend. And actually, I only selected the significant trend area. So using the Mann-Kendall test and looking at conditional rain rate decreasing trend. Actually, I don't know why it is, except for the ITCG. Actually, except for the heavy rain rate region, conditional rain rate decreasing trend. So otherwise, not significant change over the tropical region. So that, and maybe we can, compare with other trend analysis results, and also, unconditional rain rate. There are several. For example, here there is an increasing and decreasing trend, and generally, decreasing trend is appeared here. But looking at comparing with radar and other precision product like a GSMAP, GPCP, IMARCH. So comparing with the radar observation, general trend is similar, but maybe there is more like a increasing trend over this Eastern Pacific region and Maritime continent. And actually, IMARCH shows a little bit, larger amplitude, and but GSMAP is also shows an increasing trend over the Maritime continent, like this. And so, to reasoning that kind of precision trend, I checked or examined some type of high trend. This actually, I set several threshold, 20 dBz threshold, 25 and 30 dBz threshold. So looking at Maritime continent, even though we increase threshold, that means storm top height of very, very strong rain rate is also storm top height is increasing over the Maritime continent around here. So that means this maybe over Maritime continent, convective activity is more active recent years. This is the one conclusion from this storm top high trend analysis. And also drop side distribution. In this case, I calculated diameter, mass-weighted diameter trend, and also not the mass-weighted diameter. This is we call epsilon. It's a proxy of the diameter drop side distribution, and increasing trend is actually drop size becomes smaller droplet, and the decreasing trend indicates drop size become larger. So considering the higher radar reflectivity factors and looking at over the Maritime continent, these decreasing trend, that means drop size distribution become slightly larger, become larger recent years. But yeah, actually now I'm actually found several issues in the connecting the trim and the GPM data. So I'm now re-examining the overlapping period between the trim and GPM. And let me move on to the future mission. This is a PMM precipitation measuring mission. So our scientific aim is evolution to observe the evolution processes of precipitation systems, and also we'd like to investigate the cloud precipitation interaction, and also we'd like to improve the global precipitation map. This is a actually developed by JAXA, and we are joining to the NASA's AOS, Atmosphere Observing Systems mission. Actually, NASA recently changed the name AOS to Falcon. Anyway, so the launch period will be 2029 or 2030s, so that we may have at least 1 year overlap with GPM. And in PMM, important thing is that we have Doppler radar, but we don't have Ka band radar, no longer dual frequency radar. But so Doppler velocity measurement is only in radial direction, but we also have a scanning capability like a GPM or TRIM to observe the relatively wide swath observation. And right now, this satellite is in critical design phase. And this is an overview by NASA that AOS systems. So there is an inclined orbit. So we are joining to the inclined orbit with 2 satellites. One is a PMM JAXA satellite. The other one is actually France Space Agency. It is called CNES. It will launch the microwave radiometer satellite. So we are also aiming to do a delta T observation to see the development processes of the precipitation. And also some synchronous orbit, NASA will going to develop the cloud radar and backscattering radar, and together with some passive IR observation by Canadian Space Agency. Yes, yeah. And talking about back to the purpose of PMM, this is another aspect of the science, more like a science question about PMM, is one is the convective dynamics after structure of thunderstorms and tropical cyclones. And second one is the cloud precipitation processes, understanding the global precipitation systems, including micro physical processes, and also improve the GSMAP product. And also, third aim or purpose is a climate response of the precipitation. That's a long-term trend of precipitation, as I shown previous slide. And talking of these 2 items, for example, actually Gupta et al. 2023, they did a numerical simulation combining with what kind of precipitation particle formed with cold-based cloud or warm-based cloud. Actually, this figure only shows a cold-based cloud case. So that in their numerical simulation result, even though the similar precipitation systems with similar abstract structures, but the cold-based cloud is occupied or contributed by the cold rain process. That means the ice phase process, dominated to the surface precipitation. But if they did warm-based cloud case, they found that warm rain process were dominated to the precipitations. So maybe we can clarify, actual observation by PMM. And so now we are doing a similar, a kind of observation simulation of Doppler velocities. So this is one case of the typhoon simulations done by Canada-san in ISEE. And so, this is actually, there are several information of Z Doppler velocity or W and attenuation information. Well, I don't think this is Z. Anyway, not this is, maybe this is Doppler velocity, but looking at along vertical structure along this line, we can observe that kind of GM. Actually, there is a little difficulty to make a conversion so to the ice water content to snow drop size distribution. So the a little higher reflectivity simulated in typhoon, and in the simulation we can get that kind of vertical air motion like this. So the strong updraft existed maybe along this convective cloud, at a convective cloud like this, and then we assume the terminal home velocity of the snow and the precipitation. Maybe we can get things like this profile or by the PMM, so we can get like this kind of updraft region like this, and also below the melting layer we have. Actually, it looks like terminal hole velocity or the precipitation particle are dominated, but maybe we can retrieve. Final goal that we retrieve this W structure from this Doppler velocity information. And,
Sensei, sorry to interrupt you. So you have 2 minutes remaining.
Oh, really? So let me. I have 5 or 6 more. So let me go quickly, and I'd like to quickly explain about ASCII satellite. It was launched 2 years ago, and it equips Doppler velocity observations. So we can get similar pattern in the previous slide. Maybe I'll skip the ESA's video, and sorry, and also I'll skip the JAXA's video. So maybe I can give you the PowerPoint slide, so you can take a look at this slide, videos. So, and CPR has is a cloud profiling radar, and it has a 2.6 meter diameter antenna. So it's a really big antenna, and it's really higher sensitivity. If you know that CloudSat, actually it is 6 decibel better sensitivity than CloudSat, and we have Doppler velocity measurement capability, and we have observation range is up to 18 kilometers in tropical region. And so I'd like to show this one example of the wave echo observed as ASCII. Actually, this is not a tropical region, but Greenland region here. And the bottom panel shows the radar reflectivity factor of the cloud radar, and the top one is the Doppler velocity. So red one is the upward motion, and blue one is the downward motion. So up and down, up, down, up, down, that kind of wave structure first observed by the ASCII CPR from space. So actually, this is a maybe if you see the cloud images, maybe we can see some cloud streaks like this, and we can right now conclude this is induced by the orography. So the mountain, it will be a kind of mountain waves, and we can calculate, analyze global distribution like amplitude, wavelengths, and occurrence. Actually, occurrence is mainly occurred. These waves structure appear over high latitude region like Antarctica or high latitude, Arctic region, but also the tropical region. Actually, even though that deep convection gives gravity waves, it is reflected in the cloud structure, and also we can observe the really weak echo, like maybe fog, or I don't know why. What is what we observe now, but anyway, we can get a really weak echo. So if you are interested in the fog observations, maybe ASCII is also interesting or giving good information, and we can also get some. I compared with ASCII and CloudSat, how many we can detect the very, very weak echo, but CloudSat cannot detect, actually always miss the very weak echo in this, and this is a summary. So maybe I'd like to skip this one. And so if you are interested in the information regarding GPM ask here, please visit JAXA's several sites. Now, okay, thank you very much for your attention.
Okay, thank you very much, Takashi Sensei, for your perfect presentation. So now I welcome any participants who wants to ask questions. You can just turn your video on and unmute your mic, or you can also use the chat feature of the Zoom. So please, you can start now. So we have around 5 minutes for question and answer. Any questions? You can raise your hand to ask.
Mas Ardi,
Ya,
kalau nggak ada yang nanya, biar saya. Wendy.
gimana Mas? Wendy,
Wendy.
oke sih, silakan. Silakan. So please, Wendy-san, you can ask.
Okay, thank you very much, Dr. Ardi. Takashi Sensei, thank you very much for your very nice talks this morning. I got much knowledge now. Yeah, maybe we met sometimes in in the meetings. So, Sensei, I'm very sorry, but my question is relatively not fundamental, but I just want to but maybe I'm curious when we can maybe the precise question, when we can get like the operational satellite for the precipitation. Yeah, as we know that we have like GPM, TRIP, or aircars, but this is a polar satellite. As we know that precipitation cloud system is like we don't have much time to how to say to carefully check them for the specific region. That as we know that hydrometrical disaster is increasing now due to the very heavy rainfall. Then of course we need to know how we can how to say how we can get the near real time of the precipitation our cloud system that we can use for the operational purposes. So I'm very sorry for the
Yeah.
That's my question.
Yeah.
Thank you,
Okay.
Sensei.
Yeah. Thank you very much for your question. Actually, actually, issue of the spaceborne radar is sparse sampling. So that's why it is not suitable for the real-time assessment of the heavy rainfall events. That's why we developed GSMAP data. That is a hourly and 0.1 degree resolution data set. So hopefully, you can use the GSMAP data for your purpose. And maybe the radar data can be utilized for more like a climatological research and also the process studies of the heavy rainfall events, because we can get a three-dimensional structure. Yeah, so please use both the radar data and the GSMAP data.
Yes, thank you, Sensei. Can I follow the question, Dr. Adi, or maybe others has another question? If possible, I just want to tell Sensei that yes, Indonesia is a developing country. Then we don't have like good radar network like Japan, like we have X-ray. So this is our problem. That's why we asked. I'm asking about when we can get the satellite for the operational purpose. That I think will help us to monitor the occurrence of heavy rainfall in a specific region. So I'm sorry, Sensei.
Yeah.
Mas Ardi. Yeah.
Yeah, so there are several ideas about frequent observation or utilize satellite for the operational purpose. So that means that we need more satellites to observe. I mean the rain satellites. So as JPL, as I introduced in the earlier my presentation, JPL has developed 3U CubeSat radar. So actually, they have no scanning capability, but in near future, maybe we can develop very inexpensive, very cheap, scanning radars from space, so that may cover the outside of the range of your Indonesian radar network.
Okay, Sensei, thank you very much.
Okay,
Dr. Ardi.
thanks.
Thank you, Dr. Ardi. Thank you very much.
Okay, thank you, Dr. Wendy. So now I would like to give chance to Dr. Sharif.
Hello, nice to
Pak Sharif, you
see
can
you.
ask your
Yeah.
questions.
Can you hear my voice? Good. Thank you, Professor Nobu. So I'm not expert in this area, so I'm asking a very naive question. So we know that the role of errors in cloud formation is not really very clear. Given that you already provide us with some kind of information of how we observe this precipitation and cloud profiling radar, can you give us some overview of, let's say, I want to ask, can we now understand that we can study the errors or impact on the formation and later on the precipitation level?
Yeah, so you don't have a lot of chance to get the data. Not that means that hourly data, you cannot get hourly data of the from the radar, but you can actually typically a lot of researchers using them to accumulate radar data information. So certain area you are talking about oceanic precipitations. So more like a characterizing by the more it's let me say that this is more like a statistical characterization of the precipitation certain area. So that this is one typical approach using a spaceborne radar data. Is it the right answer to you, or I'm misunderstanding your question?
Yeah, let's say you presented like Earth-Care satellite radar.
Oh yes, yeah.
Yeah. Can it provide us with the size distribution of errors in the atmosphere?
Oh, yeah. The Earth-Care satellite, for the weaker rain rate, they can provide drop size, and also they can provide a cloud drop size, like an effective radius of the cloud. Actually, they have not only the radar but also the LiDAR data. So combining these two, they are providing the effective radius information. And if you visit, ASCII algorithm site, you can find that there are several products from ASCII.
Okay.
Yeah.
Good. Okay. Thank you.
Okay.
Okay, thank you, Pak Sharif. So actually, we have questions on the chat. So this is from Dr. Ginaldi Arinugroho. So he asked about if there are any previous research or preliminary study that verify the Earth-Care Doppler velocity with ground-based radar. Sensei?
Let me.
So on the chat. So he asked about any previous research or study to verify the Earth-Care product with ground-based radar.
It's a good question. Actually, we just started, actually after the launch, we started to evaluate the Doppler velocity information, but not so much, coincidence observation existed. actually, ASCII is the only nature-looking radar, so we are expecting, fly over like, if you know the emulator site or EAR site to compare the, direct comparison of the Doppler velocity data, but unfortunately, we don't have enough data to compare the Doppler velocity information. So if you have chance to have a, Doppler radar to looking upward, please, compare with ASCII, even though, it's not the, exactly overflight data, but maybe you can compare with statistically if the satellite, flies, nearby your site.
Okay. So I think we can move to another question. So I think Sophia-san from IC also want to ask question.
Yes, Sensei.
Okay.
I want to ask question regarding the GS map and I merge. Sensei last time, Sensei before this mentioned that you compare KU, GS map and I merge, and GS map is much better to compare with KU band. How about the ground-based radar, Sensei? For example, Sensei have tried to compare between ground-based radar in Japan with GS map and I merge, and which one is better?
Unfortunately, I didn't do the comparison with the
Oh.
ground-based radar
Yeah.
rainfall estimations, but just the people has already compared with JMA's radar network data with GPM DPR product. They are, almost within, I don't remember, 20% or 30%. Yeah.
I see.
Yeah.
Thank you, sir.
Okay. Maybe any other questions for Takashi Sensei? Okay, so if there are no more questions, maybe we can move to another presenter. So thank you, Takashi
Okay.
Sensei, for
Thank you
your
very
time.
much.
So, ladies and gentlemen, now we can move to the next speaker. The next one is Dr. Sophia Lestari. Now, Sophia Lestari is the graduates from the University of Melbourne. And now he is a senior researcher of the Research Center for Atmosphere and Climate of BRIN. And currently, he is a postdoctoral fellow at the ISEE Nagoya University. So, Sophia Lestari, Sophia-san, please, you can start your presentation. You have 15 minutes talk and 5 minutes question and answer.
Yeah, thank you, Adi. Yeah. Can you see my screen? Okay. So, Assalamualaikum warahmatullahi wabarakatuh. Good morning, Ibu Bapak. So my talk today is just preliminary results to understand how the different of rainfall type during the MGO phases over the maritime continent. So this work is part of the collaboration between BRIN and also with Professor Takahashi from the ISEE. So what's actually the motivation with studying about the Indonesian rainfall type difference over the, especially over the Western Java and Sumatra Island, where that I focus on my study, because over the maritime continent in general, the diurnal cycle of rainfall is always has the persistent bias. For example, like this is the model simulation and this is the observation for TRIM. This is the hourly rainfall rate. And we can see there is a high precipitation over the lane, especially here, observed by the warp, but it's quite overestimate compared to the observation here. And if we see how the average of rainfall over the land, this is the case for the Java Island. So y-axis shows time of the day, and x-axis shows the phases of MGO. I think everyone might know that the MGO, Meridional Oscillation, is the large-scale oscillation passing through Indonesia and also has the 8 phases, 1 to 8. So this is from model simulation. This is from the TRIM observation. This is also CMOF observation. We can see that the peak of the rainfall observed by the warp has the 2 peaks, while observed by TRIM and CMOF satellites, TRIM satellite and CMOF, they have only 1 peak. So from this picture, we can indicate that the models captures inaccurate phase of the peak of rain rate during the MGO. And then other results comparing the WRF or model with the observation is that, for example, this is Sumatra and Borneo. The y-axis show the average rain rate hourly, and y-axis show the time of the day. So dashed line show the average of rain area, and the thick line and this light line, the thick shows the observation, the light line shows the WRF or the model. So we can see here that the peak of the rain rate shows by the model and also by the observation has a quite different time lag. For example, like observation captures the peak 1 hour or 2 hours after the model. Especially for the Borneo Island, we can see here that the peak of the rain rate by the observation is around late of night, but by the by the model, we can see that the peak doesn't exist, but instead it's getting lower in this time. So from here, we can see there is an error in timing of the global precipitation, and maximum 4 or 5 hours, indicating that the separating rainfall type is very important to correctly simulate the phase of the diurnal precipitation cycle, especially over the maritime continent. So the current challenges is that over the Indonesian maritime continent, we have very complex topography, but we have very sparse data sets, and there are very little research about types of rainfall, while the structures of deep and shallow convection is very important across the model experiment, and this also is important to be as a main contributor for differences in timing and the spatial distribution. And in big city over the IMC also prone to severe floods and influenced by the MGO, as I mentioned. But so far, not many studies try to investigate the fine-scale spatiotemporal patterns over the Indonesian maritime continent, especially for the rainfall. So here is our study area. It's only in the western part of Jakarta, is the Western Java and also Sumatra Island. And the key question is that how the convective and stratiform rainfall changes on diurnal and seasonal scales over the Sumatra and Western Java observed by the GPM-DPR and also CBN Doppler radar datasets, and how this rainfall type changed during the strong phases of the MGO. So we use the GPM-DPR to frequency, KU and KA from 2014 until 2022. And then we aggregate this data, including reflectivity and storm top height, into 0.1 degree grids. And also we use the CBN Doppler radar already quality control for 4 years. And we define the strong MGO phases. As I mentioned, we have 8 phases. So we only selected the amplitude greater equal to 1 millimeter following the Wheeler and Hendon 2004. And for the active MGO is when the MGO or the cloud propagation exactly over the Indonesian maritime continent. And for the suppressed MGO is where MGO before coming through Indonesia, that is over the Indian Ocean, and also after passing through Indonesia, for example, like in the Pacific Ocean. So here is some of the results. So this is, we try to calculate how the spatial distribution of hourly near surface rainfall observed by the GPM DPR. We call it conditional, meaning that we selected only greater 1 millimeter per hour because we want to concentrate the rainy days distribution. So this is during the DGF or wet season. This is during the dry season, JJA. We can see for the DGF, the peak of the hourly rain rate is quite widely distributed compared to the dry season. For the dry season, we see that the peak of the rain rate or the higher rain rate occurs of the northern part of the maritime continent compared to the southern part of Indonesia. And how about the frequency of rainfall? Frequency is the occurrence of rainfall greater than 1 millimeter per hour. So it's very interesting that for the dry seasons, even though there is a low total intensity amount, but the frequency is higher. So what does it mean? We assume that during JGA, even though the low intensity appears, but the occurrence of the rainfall happens much in the southern part of the maritime continent, but the intensity is very low or lower compared to the northern part of the Indonesia. So here, so the high frequency here is actually related with the low intensity, indicating that rainfall in the southern region is dominantly characterized the more frequent but lower intensity rather than being dominated by the high intensity like rainfall in the north. And then how about the climatology of frequency stratiform and convective pixel? So this is a stratiform distribution. This is the convective distribution. This is during the wet season, and this is during the dry season. We can see that during the DGF, where it's wet season, there's more occurrence of the stratiform widely distributed. For the DGF convective, particularly the high occurrence occurs in the north and also in the south. But for the convective one during the dry season, it's interesting that the more occurrence or high occurrence appear in the southern part of radar domain. We can see from the previous one that there is also frequent more high rainfall here might be associated with the occurrence of the convective rainfall in the southern part of the IMC. And how about the different of stratiform and convective distribution during the MGO? This is the active MGO when the MGO is exactly over the Indonesia, and this is the suppressed MGO when MGO not passing through Indonesia. So this is the DGF, the upper two level, and this is also DGF, but this is also for the convective. This is JGA and this is JGA. So the main points from here, we can see that during the active MGO compared to the suppressed MGO, we can see that much more widely distributed of the stratiform rain rate and much more higher compared to stratiform suppressed. But the most interesting is that during the active phases, we can see that the high occurrence of the stratiform rain rate appears in the northern part. And for the convective one is the increased occurrence of the rainfall rain rate occurs in the southern part. This means that MGO appears, especially in DGF, contribute to less to convective rainfall events compared to GGA. And how about the frequency of surface rainfall and mean storm top height? So this is the climatology of the occurrence of the rain rate. You can see there's a high peak here around the northern part of the Java Island. And this is storm top height greater equal than 18 dBz during climatology. And then during the active MGO, this is during the suppressed MGO. We can see that during the active MGO, that the storm top height, it means that the height of the storm is relatively higher compared to the suppressed, especially in the northern part of Java Island. And this likely correlated with the increase of the high storm height, especially for the climatology. So it's likely that active much more contributed to the high storm height in the climatology compared to the suppressed one. And then if we see for the JGA, we see that this is the climatology for 18 dBz. That is for the JGS surface landfall occurrence. We can see that the occurrence here much more related to the active phases of MGO. So it might be that the occurrence here is due to the storm top height that related to much more lower. It means during JGA, maybe it's much more related to the shallow convection related to the compared to the higher convection or deep convection. So this means in JGA much more occurrence, but it's related to the shallow convection. It's around 4 or 5 kilometers height. And this picture show the distribution of the storm top height. So x-axis show the distribution of storm top height, the number of storm top height from 0 to 75 kilometers, and y-axis shows the PDF, probability distribution function or density. So this is a DGF and GGA for the 18 dBz. So we're selecting reflectivity for 18 dBz above. We can see that over the maritime continent, in general, that the peak of the storm top height, not the peak, the average of the storm top height is around 5 kilometers. And if we move to 30 to 40 dBz, it's also similar. But if we see for the 40 dBz, like this, the red color shows that the intense precipitation course occur over the broader region compared to the blue, that's 30 dBz, indicating that the 40 dBz has a tendency of toward lower level dominance.
Sophie,
2 more minutes?
Have 3 minutes remaining.
Okay, okay. So this is counter frequency of the reflectivity during active and suppressed MGO. This is over Sumatra, this is over the Java Island. And the red color shows the high frequency. So in general, from this picture, we can see that stratiform over Sumatra has higher frequency compared to the Java Island. You can see this is the higher compared to Java Island here. But rainfall over Java is more strongly influenced by local topography and land sea based processes. And during suppressed phases, we can see that in DGF, sifat show high frequency along with the stronger bright band, a little bit here, indicating more frequent and deeper stratiform rainfall on more organized systems. And the most interesting point is that over Java Island, we have 2 peaks of the high occurrence of reflectivity that might indicate that this peak shows the initiation of the convection, while the second peak here shows where the deep convection occurs. So this is a comparing only for the ocean in the north Java Island, and in the west, this is active and it is suppressed. So we see during the suppressed, even the MGO not coming through Indonesia, we already has a very deep convection, especially in DGF, especially for the northern part of the ocean over Java compared to the west. And this is over Sumatra. We can see that the deep convection is not too high compared to the western Java Island. The frequency much more in the below. So this is the figure shows how the stratiform pixel close each other with the convective. So we want to know whether the stratiform occurs when the convection also happens there. It means that when there is the infill convection, whether the stratiform also comes from that. So we see that during the DGF suppress MGO and active, this one, the dashed line, we found that the closest distance with stratiform convective brain rates is lower percentage during the active. So it means during the active MGO, the stratiform brain rate is much more widespread and related to large scale, while during the suppress is the stratiform is come from the isolated convective because they close each other. And this is about the diurnal peak of brain rates observed by the weather radar. So this is during the climatology, this is suppressed, and this is active MGO. So dashed line show the stratiform, solid line show the convective. So we see focus on the suppressed and active MGO. So during the suppressed, we can see very clear difference of the peak of the rain rate during the morning and also in the afternoon. It's very clear, while during the active, it's not too much different, indicating that the suppressed MGO phase, the diurnal phases, is very strong compared to the active phase. So this is a summary of our work to date. So the first is the stratiform is dominant rain rate during the MGO, and MGO has larger influence of stratiform and convective brain rate, indicating that the maritime continent is strongly affected by the largest system of the MGO. And stratiform of Sumatra has a higher frequency than over the Java. And stratiform brain rate is higher during the active phase. And it seems that not related to the diurnal cycle. And in DGF, the stratiform brain rate in the suppressed phases could be related to the stratiform anvil of the isolated convection compared to the active phase. I think that is all, Pak Ardi. Thank you.
Okay, thank you very much, Sophia, for your nice presentation. So now I welcome any question from participants. Because of limited time, maybe only one question.
Sorry.
So yeah, you can ask now. No problem. You can also write on the chat feature of Zoom. Any questions? So if there are no questions, I would like to ask one question to
Yes.
Sophie. So so did you consider some study suggest the vanguard effect before the MGO comes, right? So did you also consider this kind of effect when you analyze this data set?
Yes, we will consider that. For now, not yet, because we did only just comparing the ocean and the Sumatra, over the land, but not yet west and the eastern part. If we if we divide it between Western and Sumatra Island, maybe we can see the effect of vanguard, right, Adi? For example, maybe in suppressed space, the western part of Sumatra is much more higher peak of rain rate compared to the eastern part. But now we are doing only general land over the Sumatra, but not yet divided between the eastern and western part. But I think we will do it and try to divide between the two so we can see the effect of that vanguard that you mentioned.
Okay.
Yeah.
Okay, thank you very much. So any other questions? If there are no questions, maybe we can move to next presentation. So thank you, Sophia, for your presentation. So
Thank
next
you,
So next we will have Dr. Wendy to give the presentation about his research. So Dr. Wendy is a graduate from the Kyoto University, and I think now he is focusing on the radar and also satellite observation for rainfall. So, Dr. Randy, the time is yours.
Thank you very much, Dr. Ardi. Can you hear my voice and clearly see my
Yes.
slide? Okay, thank you very much. Yes, good afternoon, everyone. Yes, let me introduce myself. My name is India Jupa. As introduced by Dr. Ardi, then I'm a researcher in the Research Center for Atmosphere and Climate. So today, in this very nice moment, I would like to share our research. This research is collaborative research between the PIMA, Center for Climate and Atmosphere, with the DPRI, hydrometeorological disaster, with Nagoya Sensei. Then, yes, of course, some stuff in the PIMA. So the title of my presentation is Warm Rain Dynamics and Microphysical Variability during the winter monsoon over ocean and land and their future change in West Java, Indonesia. So mostly my talk will be about warm rain and using modeling data because of the limitation time. But please let me introduce first about the warm rain. Yes, warm rain is the rain which form from the cloud which occur below the freezing level. Then mostly the occurrence of warm rains is due to collision and coalescence. So it's due to by the high moisture and a strong updraft. And yes, of course, in Indonesia, in the tropics, based on the yeah.
Sorry.
Yeah.
I cannot see your screen.
Really?
Yes. Now we can see. Okay, thank you. Just continue.
I cannot make a slideshow. Okay, but this is clear. Is it clear now?
Yes, this is clear now.
Okay, thank you very much. Yeah,
Yes.
in the tropics, warm rains account for the 71% of the total rain amounts and 72% of the total rain area. Yes, because of Indonesia is surrounded by the ocean. Then the objective of this research is to investigate warm rain dynamics and microphysical variability in the West Java region during the winter monsoon or December, January, February, and their future change. So this is our research locations. Yeah, as you know that during the monsoon we have like compound flooding in the West Java, especially in Jakarta. Extreme rainfall and of course the irrigation or something like maybe also the river flows from the Bogor and many kinds of things. So it is very interesting to study this region. So, but our research focus for the warm rains occurrence for this area. So in this research, we use the MRI AGCM 3.2 data, which are simulated by the MRI GMA. Then this data included by the G4PDF data. And then we use the reanalysis data, ERA 5. Then for the validation, or we use the GPM and Himawari data. So I'm very sorry, I do not put any slide for the validation for this research, but this research already published. Then I kindly encourage everyone to read this paper. But the conclusion is during the December, January, February, or winter monsoon, we have like the increasing of the occurrence of warm rain in the Western Java or Western Indonesia, especially also in the Jakarta region or Java Sea. So these 5 figures is the average 30 years average of the warm rain occurrence. So this data, this is the model data, MRI AGCM data, but we had validate this data by using the TRIM data for 70 years TRIM data by using cloud liquid water content observed by the TRIM satellite. So now we can see by every 30 years the increasing of the warm rate or cloud liquid water content, which can be used as the proxy of the occurrence of warm rate. So we use the cloud liquid water content observed by the TRIM satellite to validate the cloud water content simulated by the AGCM to see the occurrence of warm rain. So as you can see here, the increasing of the occurrence of warm rain in the Western Java of Indonesia. This is the trend line of the occurrence of warm rain. So the red is for the average for the Indonesia region, and then the blue one is for the Java Sea, and then x-axis the 150 years simulated data, and this is the value of the cloud liquid water contents. So now we propose that in the future, based on the validation of model data and TRIM satellite data, we propose that in the future, the occurrence of warm rain, which means also the lower or the effective rainfall will be more active than more occurrence in the future. So in the next slide, we want to investigate more why it happens. So this is data. This is a meridional data obtained by ERA 5 for 60 years. The upper figures is the 1950 to 79. This is average for 30 years, and then the below one is average 30 years. For the next period, 30 years, 80 to 2009. So here we make a trend lines. This is the spatial trend line for the 60 years. We can get that the increasing of meridional winds during the winter monsoon. So this is I make an average for the two regions, the blue one and the yellow ones. The blue one is the Hattori. As we know that Hattori in 2011 proposed that heavy rainfall occur in Jakarta is due to by the increasing of the southerly winds in this region. So in the future, so this is 60 year. This is the ERA 5 data, past data, but for this region, not relatively decrease. So what we will see what the model data can show us that another perspective data. So for these slides, so we try to make a phrase for this model data, AGCM data. This is every 30 years of the southerly wind data. And then we found that the increasing of the southerly wind during the winter monsoon, then the regions approach to the moorland area. Then this is the previous slides, the increasing of the southerly wind. But this is model data, as we know that by using ERA 5, the previous data, the average for 60 years, that we don't have strong or increasing of the southerly wind in this region, in the yellow part region. This is a Java Sea region. But if we average for the during DGF for the 205 hectopascal for the 150 years data, so we can see that the increasing of the southerly wind in the Java region, of also in the Jakarta area. Then we try to check the dynamic of atmosphere by using the K convective inhibition and temperature lapse rate. By using in this part, we just try by using the ERA5 data. But as we can see here, every for the next 30 years, we found that K increase in the Java Sea region and convective inhibition decrease, which means that's favorable for the convergence and convections. But once we check the temperature lapse rate, but here we found that the temperature lapse rate in the upper layer, 850 to 500 hectopascal, we have the decrease of temperature lapse rate, which means that the upper part is a greater stability, which means that maybe it can suppress the convection. Then how to say, the rain will occur more shallow in the future, or warm rain will strongly or more occurrence occur in the future. So this is also by the model data, AGCM data. This is the cloud cover. This is also the average for 30 years of the cloud cover. Then this is the trend line in the below one. And as we can see here, this is the average of the cloud cover for the Indonesian region for the 3-layer, 200 hectopascal, 500, and 850 hectopascal. As we can see here, the cloud cover in the upper layer in 200 is decreasing in the future, but the cloud cover in the lower layer is decreasing. So which means that the cloud cover in the lower layer will increase in the future. Then we try to check the climate or the long term of the Himawari data. This is for 20 years, but this is the average for the 10 years. And then the right panel is the average for the 10 years of the albedo or B03 observed by the Himawari data. Then here we found that the increasing of albedo, which means that this more can give us insight that the cloud depth in the future will occur more times than before. Then here 2011 to 2020 is the cloud albedo is more depth than 2000 to 2010. Then we try to check this by using GPM, by the diameter observed by the GM. So this we have like 5 elevation of GM data: 1 kilometer, 2 kilometers, 3 kilometers, 5 kilometers, and 4 kilometers and 5 kilometers. So in this Java Sea regions, we can see that the DM is higher or bigger in the 3 or 4 kilometers, but decrease in 5 kilometers. That's here we found that the DM become decrease in the higher level in the 5 kilometers. We just saw the 5 kilometers because we want to investigate the warm rate. So here we found that the DM is bigger in the coastline and the windward side of the island. So as the conclusion of this research we have the increasing of southerly winds during DGF or during monsoon, but maybe we need to investigate more enhance low-level convergence, then that's why the more increasing precipitation or rainfall during the coastline in the west or in the northern part of Jakarta or Java Island. And then higher atmospheric stability will, in the high level, will suppress the deep convection. And then cloud cover decrease in the high altitude, which can give us insight or maybe information that the increasing of the increasing of the warm rain in the future, lower level clouds, and then the increasing albedo will which indicate the increasing of cloud depth. So in the next target, we are going to investigate another cloud parameters like LCL, LFC, and LNB by using ERA5 and AGCM to investigate more about the occurrence of warm rain in the future, and of course the utilization of EarthCare satellite to investigate the clouds microphysics in the maritime continent, especially in Western Java during monsoon, is very, very important. Thank you very much, Dr. Ardi. I hope my time is enough. Thank you very much for the audience, for the attention.
Okay, thank you very much, Wendy. So you're on time, actually. So I welcome any participants for asking questions to Dr. Wendy.
Can I ask a question then?
Yes, please, Dr. Sarif.
So you mentioned that the rainfall will be increasing in the next future. So if you think of the water mass conservation, so I'm wondering where the water mass coming from. I mean, the additional water mass coming from. Do you think that the increasing warm rain coming from the surface or the decreasing of the convective rains, or do you think that it's like increasing evaporations, or do you think the transfer of water mass from the other regions? What do you think?
Okay, thank you very much, Dr. Sarif. I think this is very important question related to this research. Thank you very much again. Yes, of course, as I mentioned that this research we proceed during the winter monsoon, which means that the weather vapor mostly bring from the northern part of like from China, Tibetan or something, or China Sea. This this moisture coming from those areas. Then during the winter monsoon, we know that much weather vapor or moisture coming from those areas. Then we'll, of course, in Indonesia we have like of course we have a tropical and very strong solar in the daytime that will trigger the moisture, the high moisture to be precipitation. So I think yes, my short answer is of course the moisture coming from the those area from Tibetan or something during the winter monsoon, and the occurrence itself, which is whether it's from the convective or convergence, we are not investigated yet. But of course, this will be our next target to see it by the LFC or another atmospheric parameters. My answer, good, Dr. Sarif, or can answer your question.
Yeah. Thank you for the answer.
Thank you very much, Dr. Sarif. Okay.
Thank you, Dr. Sarif. And now I think Sophia also want to ask questions. Sophia, please.
Oh, Wendy, thank you for nice presentation. Yes. Can you hear?
Yep.
Yes.
Yes. So, Pak Wendy, regarding you said that you are going to use the ERA 5 for your next research. I was thinking that the resolution of the ERA 5 is quite lower compared to other observation data set, while our Indonesian regions features, especially for the rainfall, is very local. Do you think that the ERA 5 is quite good enough to capture that kind of the local features over the Indonesian maritime continent, given that the local one usually is around 5 kilometers, 10 kilometers? Do you have any idea about that? Especially in investigating the cloud
Yes.
dynamics. Yeah.
Okay. This is very hard question, I think. Yes, of course, we know that ERA or model data cannot give us very nice resolutions, but we try to make our previous research. We try to downscale the ERA and model data to make it more nice resolution. But of course, the result, how to say it? Yes. I think it is quite tricky to answer that the ERA 5 can give us a good result for the micro scale of Indonesia. Like, for example, like maybe convective clouds, maybe around 10 kilometers or something that maybe ERA cannot get it. But we try to make to downscale it, and of course the model data itself. I didn't mention in the slide, but we have like NHRCM. This is also climate model data with 5 kilometer resolutions. That possibly that I'm going also to use it. But ERA 5, we use ERA 5 because the ERA 5 is already validated by many researchers. So this is like to be safe to use ERA 5 first. Before we continue by using the new data set, especially for the climate data sets. But yes, now we have like long-term satellite data like TRIM or GPM that of course maybe can give us or help us to make a dynamic downscale of the ERA 5 or statistically approach. Maybe I think my answer, Dr. Sophie, I'm very sorry. Your question is very difficult.
No, thank you, Pak Wendy. You answering the question. Thank you.
Thank you very much.
Because our limited time, I think we should move to another presenter. So thank you, Dr. Wendy, for your nice presentation.
Thank you, Dr. Adi, everyone.
So for the next presenter, we will have Ms. Rahmawati Shahdiza from BRIN. So Ms. Rahmawati is the graduate from University of Reading, and now he will talk about the microphysical properties of tropical cyclone Senyap outer advance, which was happened like last November. So Rahma, the time is your answer.
Thank you, Mas Aldi. Also, thank you. Morning for the ladies and gentlemen. Thank you for the opportunity to present our work. In cloud physics and its application research group. I will share my PowerPoint slide. Is it visible?
Wait a minute.
And if my voice sounds clear?
Yes, your presentation and voice is clear.
Okay, because my slides is more than the allocated time, I will move directly to the next slide. This is our research background and aim. So our research is focused on the tropical cyclone Senyap, which formed in the late November in 2025. in the narrow Strait of Malacca. Despite the relative distance of West Sumatra with the TC core at around 400 kilometers, but the BNPB report stated that the West Sumatra area is heavily impacted by this tropical cyclone, as it's cited here. There are around 267 death toll, and 70% were still reported missing. Here we also attach several documentation that we curated from various sources to give a glimpse of how devastated the TC in West Sumatra alone. And then, as we see from the report here, Agam Regency is the major area impacted in West Sumatra. Therefore, in the study, we'll use data from Kota Tabang sites, which is located in the Agam Regency, to understand the macrophysical properties of the tropical cyclone Senyal. The tropical cyclone system is a complex system, and the organization structure usually classified into the inner spiral rain band and the outer rain band. The outer rain band usually located at around 150 kilometers in the radial distance from the TC core, and it could propagate to 500 to 600 kilometers, or in some cases it penetrate to outside of the operational alerts area of the TCs. But despite being far from the core, this outer rain band can produce intense rainfall and significantly influence the cyclone evolution and surface precipitation, sometimes leading to severe weather, as we've seen in the West Sumatra, or in some cases reported could exceed the severe weather in the TC core. To our knowledge, there are no related study about the TC microphysical characteristic has been done in Indonesia area, particularly for the TC outer rain bands. This is probably due to the scarcity of the ground-based observation. There are a number of previous studies about tropical cyclone in IMC, which largely focus on the dynamical process or precipitation distribution or the different global phenomena, which is mostly relying on the satellite or numerical models. This is some of the example of the previous studies. Therefore, in the study, we'll analyze the microphysical properties of the Senyal outer rain bands using Kota Tabang site. For this tropical cyclone Senyal, actually Abdillah et al. 2026 already discussed about the synaptic scale drivers, and they have extensively studied the drivers of the TC Senyal. So we will not furtherly discuss this here. This is for the study, we use several data, which is first is the primary data, use the Parsifal discriminator in Kota Tabang site, which provided 1 minute sample, and then the IB tracks data from NOAA for the cyclone tracking, and then the Himawari 8 temperature black body from the ER1 channel. This will be used to analyze the cloud top temperature, and then the ERA5 hourly single levels and pressure levels. And then this is for information that the Kota Tabang site located at 865 meters above sea level, located in the Barisan Highland as shown in this figure by Marzuki et al. 2021. In the top panel is the Parsifal discriminator in Kota Tabang. The method that we use is, the first one is to identify the TC outer rain band, and then we quality control the discriminator data, and then we calculate the drop size distribution parameters and analyze the microphysical properties. This is for the outer rain band identification, we use previous studies. Based on previous studies, the structure of the outer rain band could be an extended rain band from the spiral rain band, or a could be like a convective cells, like shown in this one, which is not linked from with the inner core, or it could be also like an embedded stratiform and convective, as shown here or here. For our case for TC Senyar in Kota Tabang, we try to approach with different methods. First one, before we started, we would like to emphasize that the IB tracks data is showing the tracks for Senyar is started from 25 November 12 UTC to 28 November 12 UTC, but the digital metadata only available from this green dot, which from 25 November 12 UTC to 26 November 21 UTC. And then the track and the distance of the plot here in the green square shows that the distance from the the TC core to Kota Tabang is around 400 to 600 kilometers, which sits within the outer rainband regions. And then we try to analyze the Himawari 8 temperature black body for Kota Tabang area, as shown as the red square here. In general, the plot top temperature slightly warmer if compared to the TC core in the northwest of Sumatra. This indicating a little less convection if compared to the inner core. And then the band structure here in Kota Tabang, it followed the characteristic as stated before, that it embedded. I'm sorry. It's extended toward Kota Tabang station, and it looks like the structure looks like a stratiform with or embedded convective rain band. And then we try to analyze the ERA 5 hourly single level and pressure levels data for the vertically integrated moisture divergence. Here, the negative value indicating the convergence in Kota Tabang area and the TC Senyar's area, indicating high moisture supply, while the mean wind in Kota Tabang here, indicating that Kota Tabang area affected by the cyclonic wind originating from the northwest. A strict quality control for the digital metadata is applied to this study to eliminate the spurious raindrops, low signal-to-noise ratio, implausible point of the unphysical data, and to reduce the statistical and quantization errors. This method is well established, as it used by numerous study. Some of it is Marzuki et al. 2013, Janapati et al. 2020, and Rangono et al. 2025. This is the quality control of the data. The x-axis is diameter, the y-axis is the fall speed of the drops. Our filtered data largely centered around the atlas, as shown in the black line. And when we compare to Marzuki, which is also in Kota Tabang area, Kota Tabang site for non-TC rain with longer data period, which will be used here as the climatology base, shows that the scatter similar for smaller drops, but our results slightly higher for the higher fall speed velocity. This mean error bar, which is deviate from atlas, actually is consistent with previous study about TC rain bands in China, and Frederick et al. In 2013 link it to might be caused by the downdraft or turbulence effect, which is more stronger in a tropical cyclone rain bands. and then combined with the force with the orographic effect in Kota Tabang, since it's located in highland area, so the air mass is force lifting, which might enhance this deviation. This is to produce the drop size distribution parameters as shown here. We will use the gamma distribution equation as shown by these equations below. This is the results in the discussion. Here is the time series of the data during the tropical cyclone Senyar. This blank area is no data. Because since this 21 UTC 26 November, there was a blackout, so all of the instruments in Kota Tabang area could not operate. The x-axis is time, and the y-axis is diameter in the left panel, and then in the right panel is the rain rate in millimeter per hour. In general, the rainfall in Kota Tabang during TC Senyar characterized by the intermittent bursts, which indicated by the black circles. And then if we look at closely, the earlier phase is dominated by the smaller drops, which is shows by the red square. And then while the larger drops from 3 to up to 6 millimeter have with peaking high intensity exceeding 120 millimeter per hour. This is for a 1 minute rain. This intermittent burst further confirm previous slide that the alternating stratiform, the structure of the rain band is alternating stratiform and embedded convective precipitation. This is the plot. This plot is the mean raindrop concentration, ND for the y-axis with the diameter. And then we classified the rain based from very light rain to extreme rain. In general, it shows a clear rain from light rain, the cyan color, to magenta, to extreme rain magenta, which is as the spectrum broaden to higher to broad diameter, the slope is flattening, while this one is more steeper. Also, there is a high concentration of small raindrops. This is aligned with Bao et al. In outer rain band in China, Wang et al. Or Marzuki and Rengono. So, but what's different with Marzuki is the end tail here, which indicating the contribution of large drop during the tropical cyclone Senyar is higher than the climatology base. And when we compare to Rengono et al. 2025, which study about the extreme rain in Jakarta area, Rengono et al. Shows that extreme rain during the wet season generated from long-lasting stratiform rain, indicating here the tropical cyclone Senyar extreme rain with Rengono have different driver and mechanism. This two plot is the contribution from rain rate to the overall percentage of the TC Senyar rain band and the diameter percentage. From the panel A, we could see that the dominance is the light to moderate rain with 0.5 to 5 millimeter per hour, with contributing around 43% of the recorded rain events. While for the diameter, this is interesting because 80% of the total drop count consists of smaller than 1 millimeter, but the actual rainfall is derived from the drops between the 1 millimeter and 3 millimeter, as shown by the blue bar here. The massive number of tiny drops indicate a high active warm rain process, hint that the collision and collisions of droplets is massive in this tropical sequence scenario outer band.
Rahma, you have 2 minutes remaining.
Oh, sorry. This is the scatter plot of the normalized intercept parameter with the log with the mean mass weighted diameter. It can show that the scatter is to the left of the selective form line by Bringy, and then with more sample it characterized by by the density in this area, and then in general the trend is as the when the low rain rate, the diameter is smaller and the concentration higher, while the higher rain rate, the diameter larger and the concentration and the liquid water content also higher. This is the scatter plot of the mu versus lambda. So mu is the values from the shape of the droplets, while lambda is the slope indicating the speed of the decrease of the drop. I'm sorry. When we compare it with different previous study, there are several studies here about tropical cyclone. Senyar in Kota Tabang significantly below all the reference line from the literature, and fixed lambda that have lower shape parameter than the other TC. This is the ZR relationships. In general, all the scatters data shows sits in the close relationship with all line. But if we compare with another tropical cyclone or Mazuki, it's better to use equation from the typhoon specific like Chang for North Taiwan or Bao for Maria TCOR than using Mazuki for this for specific event like tropical cyclone. This is the conclusion. The outer rain band in Serpong shows stratiform with intermittent bursts of embedded convective precipitation, and then the higher rain rate associated with larger mid-weighted diameter, higher liquid water content, and stable lower intercept parameter. Our analysis consistently show that the dominant process is collision coalescence as the dominant microphysical process is drop growth rather than the increase in drop number concentration. And then the orographic effect in Kota Tabang likely promotes the orographic lifting and increase this efficiency. And the downdraft and turbulence inside tropical cyclone increase this process efficiency too. Here our suggestion, Abdillah shows that there are apparent increase in near equatorial TC. This implies the urgency to establish network of the hydrometer. This is that we try to plot from all of the paper about this hydrometer in Indonesia, but most of the current network is not operated. In Indonesia, the rain rate is used to measure using tipping bucket rain gauge, but it has downside that it measure low rainfall, and then it cannot detect hydrometeor. Therefore, a denser network is useful this hydrometer for TC in extreme rain events. One of the example is like what Takahashi Sensei said earlier, that this hydrometer could use to verify and validate GPM, DPR, and Earth satellite. This is for our next target. This is for the acknowledgement reference. Thank you very much.
Okay, thank you very much, Rahma, for your nice presentation. So now I'm opening the question and answer session. So if any participant wants to ask, you can just raise your hand and activate your camera and microphone. Any questions? Rahma, I have one question. So you say that on your summary, your last slide, okay, this one, that the observation site at Kota Tabang, there is some effect of the Barisan Mountains, right? Which promotes orographic lifting. And how about the one in Java? So you also know that on the southern part of Java, we have also mountain ranges like Bogor and many mountains there. So do you think there are also some effect of these mountains of
Yes.
to your result here?
Actually, this study already done by Renggono et al. To 2025, which shows that in the highland in Bogor area, the observed drop size diameter is higher than the in compared to the lowland of in Serpong area. But here in Kota Tabang, this drop size is shown, the fall velocity is higher than what is reported there, and also the drop size is likely more broad. So in Kota Tabang, during this season, probably enhanced by the downdraft and turbulence inside the TC rain bands.
Okay. Any other questions? So I have another question. So during the Senyar cyclone, so the period of the cyclone is like the shifting from the November to December, and you know December is the start of rainy season in Indonesia. So do you think there are some effect of this seasonal change to your result? Maybe because of like a monsoon surge, there's some effect of this phenomena to the result.
Maybe, but actually we haven't done analysis of in that area yet. But it's an interesting point to further study about.
Okay. Any other questions? So if there are no more questions, maybe you can move to the next presenter. So Rahma, thank you very much for your nice presentation.
Thank you.
Okay, now we can move to the next presenter. Next presenter is Dr. Anis Purwaningsih from BRIN. So Dr. Anis is the graduate from the Wageningen University. And yeah, the time is yours, Ms. Anis.
Yeah. Thank you, Mr. Adi. Actually, I haven't got my doctoral degree, but yeah, it's a praying for me. Yeah. Okay, is my voice clear and also my screen can be seen? Okay. Am I showing the slideshow or the PPT?
Yeah, it's perfect. So you can start.
Okay, thank you for the opportunity, everyone. Today in this very nice opportunity, I would like to present about NJO influence on inland rainfall variability of West Sumatra. Specifically, I would like to focus on rules of orographic effects. This work is already done and already published by Satyadi et al. In 2025. And under the research group of tropical atmospheric dynamics. So the background of the study, as we know that Sumatra Island has complex terrains. It's spanning from south to the north, and it's dominated by the Bukit Barisan mountain range. And the height is up to 300 meters above sea level. And from the previous study that Sumatra's topography play a crucial role in shaping local circulation patterns and driving convective activity with a clear diurnal cycle. As the study by Wu et al. Here, there is a clear diurnal cycle with the peak in the afternoon of rainfall, and also spatially, Mori et al. Also has a result presenting the onshore propagation of rain in the evening and offshore propagation of rain in the morning in the coastal sea regions. And related to these orographic conditions, we try to figure out how the orography and MJO interact and impact rainfall variability over this island. As we know from the previous study that the Sumatra serrans can slow the MJO's propagation from west to the east, and the MJO itself has pace dependence impacts on rainfall variability. For example, from Fujita et al., the MJO phase 2 and 3 can make a moderate low-level westerly winds over the eastern of the Indian Oceans. Wheeler and Hendon also make a notice that phase 3, 4, and 5 has significant influence of increasing rainfall in the Indonesian maritime continent, and specifically in the Sumatra Island, there is a Fangbird effect that we already discussed in previous presentations. Yeah, where this effect is where where rainfall is increasing before the envelope of MJO reaching the regions. So we try to figure out the effect of orography here. We selected 5 locations. L1 representing the coastal area, L2 representing the windward of the mountain, and L3 and L4 representing the mountain range locations, and the L5 represents the leeward side of the mountain. And we try to explore how this orography and MJO interact and infect the rainfall variability under 2 MJO conditions, MJO3 and MJO4. And the strength of this work is, one of the strengths of this work is because there is a ragam observation station located on the L3, which has several observations tools installed there. For example, equatorial atmospheric radar, optical rain gauge, the radiometer, radiosondes, and also X-band radar. To gain the aim of the study, we have 5 locations, but we only have 1 location with the observations data. So we try to firstly use the era 5 data, which has more variables to be investigated, and we try to compare the performance of era 5 in the location of L3 in Agam observation station. And for the rest, for the era 5 data, we try to make a composite of variables like precipitation, vertical integral moisture convergence, zonal wind, etc. For 22 years in 3 conditions, MJO3, MJO4, and the mean conditions. So this is the first result. This is a result from Koto Tabang side. We try to compare the observation data with the era 5 analysis data. We conclude that although the magnitude is kind of different between observation data and era 5, but the pattern representing the mean MJO, MJO3 and MJO4 conditions kind of similar. When we compare first the rainfall data from ERA 5 and ORG, the evening peak of rainfall can be detected by those two data. Although the ERA 5 has earlier peak compared to the ORG, however, when we try to calculate the R value, it's fairly good, around 0.8 for the mean conditions, 0.7 for the MgO3, and 0.69 for the MgO4. That's also can be seen for the other parameters. For example, when we compare the zonal wind data in the L3 from equatorial atmospheric radar with the vertical, it should be zonal wind from the L3 ERA 5. We also see the similar pattern, like the MgO4 has a greater wind speed over this high altitude compared to the mean and also the MgO4. MgO4 has the greater wind magnitude compared to the mean and also MgO3. With the total column of water vapor in the L3, comparing between ERA 5 and radiometer, it has a similar result. So from here, we try to use the ERA 5 data for conducting the analysis for another parameters. This first one, we try to show the rainfall variability from ERA 5. So this left figure showing the diurnal rainfall from location 1 until location 5. And the right figures represents the spatial maps of the precipitation on the three conditions. As we know that in the mountain side, the windward side of mountain has a greater rainfall magnitude. It's in MgO3, MgO4, and MgO5, and in the mean condition. But we can also see the significance of increasing rainfall in the MgO3, which is also in consistency, which is consistent with the previous study that before the envelope of MgO3 of MgO reaching the Sumatra Island, the rainfall is increasing. And compared to comparing one to another locations, the rainfall increased significantly in afternoon, especially in higher elevations such as L3 and L4. But during the night and morning hours, rainfall is more concentrated on the windward side, for example, L1 and also L2. And this contrast also, these figures are also contrasting or highlight the different impacts of MgO3 and MgO4 on regional rainfall, where MgO3 enhance rainfall and MgO4 is slightly diminishing the rainfall, particularly in the afternoon time. And then what's interesting about our result is this pattern of rainfall is inconsistent with the pattern of moisture convergence, which has higher moisture convergence in a mountain top compared to the another locations, and higher of moisture convergence in MgO3 compared to MgO4. And this higher VIMC during MgO3 may contribute to the increased rainfall, as enhanced the moisture convergence will promote the convection and then cloud development and finally the precipitation. The increasing of rainfall that is linear with the VIMC in MgO3 cannot be explained by the condition of convective available potential energy in the left figures here. We can see that the Kp, or convective available potential energy, is lower in MgO4 and MgO3, sorry, is higher in MgO3, but the inhibition, or the convective inhibition, is much lower in MgO3. So this explains that the high Kp is not correlate with high precipitation directly, but it helped the thermodynamic condition. It can be explained by the lower inhibition happening in the MgO3. And we also conclude that there is another factors maybe that make the MgO3 is more higher, has higher precipitation, which are the mechanical lifting that can be explained by the high zonal the low zonal wind in MgO3, which promotes the high moisture convergence in MgO3. And it also can be explained by the front number, where the zonal wind is one of the factors to calculate to calculate the front number. So the obstructions in the low front number in MgO4 is because of the low zonal wind. That's why make the moisture convergence is high in MgO3. When we compare in one panel on all of the variables, yeah, we can also conclude that precipitation is more related with the VIMC conditions compared to the thermodynamics condition explained by Kp and also Chin. Instead, we can conclude as well here, because of the lower inhibitions in L3 location here, that's make the precipitation is higher over L3. To sum up, we can conclude that generally the higher rainfall occurs on the mountaintop, except at night to morning when coastal area receive more rain, and this variation of rainfall is closely linked to change in VIMC. And in for the MgO3, because of the convergence area is in the Indian Ocean, in the western part of Sumatra Island, that's promote the reduce of westerly wind. That's why the low level convergence of MgO oppose the eastward zonal wind. That's why it can increase the moisture convergence over the Sumatra Island during MgO3. When MgO4, the MgO's low level convergence is already passing through or above the Indonesian maritime continent. So the MgO's low level convergence circulation aligns with the eastward zonal wind. That's why this red color of westerly winds illustrated with very bold red color representing the increasing westerly wind. And this increased westerly wind can reduce the convergence over the Sumatra Island. That's why it's also reducing the vertical integrated of moisture convergence. Our current works in atmospheric dynamics research group, we try to study as well on the controls of offshore propagation of diurnal convection over West Sumatra. We try to see the gravity waves and also the diurnal conditions, diurnal convections over West Sumatra related to the MGO condition as well. And this is in this first work leads by Pak Didi Satyadi and will be prepared for publication. And the second one related to my presentation today, there is also manuscript in preparations talking about seasonal modulations of the diurnal and vertical evolution of inland convection over West Sumatra by Maranjulan oscillations. So we try to utilize the observation data over there, such as equatorial atmospheric radar, to see the vertical and diurnal evolutions. For example, in first panel, this is for zonal wind, and the second panel, this is from era 5. This is the moisture convergence in vertical cross sections for phase 2, phase 3, and phase 4 MGO. We found that yes, there is a significant an increasing of moisture convergence in a low level during midday until afternoon during phase 2 and phase 3, where MGO's envelope is not is still in the Indian Ocean. And then yeah, we try to utilize the Himawari as well, and also ceilometer data for explaining the conditions of vertical and diurnal evolution during these MGO conditions. Okay, that's all maybe from me and from this research group. Thank you very much for the opportunity.
Okay, thank you very much, Ms. Anis, for your nice presentation. So now I'm opening the final question and answer session for this presentation. So if any other participants wants to ask question to Ms. Anis, I welcome you to ask. Any questions?
Why, can I have a simple question then? Can I have a simple question then?
Yes, yes, please.
Yeah, you mentioned that the existence of the Sumatra's mountainous area slowed down the MGO oscillation. But I might just missed it, but if you can just show me how much it slowed down the MGO.
Yeah, Pak Syarif, thank you for your question. It's actually already published by another researcher here. That I forgot the number. How kilometers? How kilometer per hour or how kilometer per day? It's slower, but maybe yeah. What I can only do now is referring these papers for reducing the eastward movement of MGO because of Sumatra's terrain. I'm sorry, Pak Syarif.
Okay, that's okay. Thank you.
Okay, thank you, Pak Syarif. And we have another question from Dr. Ari. So he asked about the VIMC. So the first question is, for the VIMC calculation, is there any smoothing process for the plotting? And the second question is, what is the physical explanation of the VIMC difference in the figure L1 to L5?
Yeah, thank you, Mr. Ari, for the question. It's a really nice question. Firstly, we directly use the VIMC variable from era 5. It's originally a VIMD, vertical integrated moisture divergence, but we try to multiply it by -1 to make it as a moisture convergence. And we only collected the data and make a composite of the 5 location for mean condition, firstly for MGO3 and MGO4. And the meaning of your second question is sorry, could you please explain, Mr. Ari?
Yes, thank you very much. For the second question, you see here from L1 to L4,
Yes.
the magnitude is different
Yes.
from A to E. Is there any explanation since it's from the south into the north? Is there any explanation, for example, due to the topographic or something?
Yeah, thank you, Mr. Ari, for the
Thank you.
question. So basically, for this moisture convergence, it can be clearly explained by the data of zonal wind. When MgO3, the zonal wind is kind of slow down, and there is there is moisture convergence over there because of normally the movement, the wind movement is eastward as well. And we can also see in the orographic effect here that when it's in the L3, there is no obstructions because L3 is in the mountain top. There is no obstructions of the mountain, but the moisture convergence is higher here than in the another location. Mr. Ari, maybe I hope it can satisfy that.
Yes. So yeah, thank you very much, because I think it's very similar with the zonal wind plotting. So probably, yeah. Thank you very much.
Yeah.
Thank you.
Okay. Any other questions? So if there are no more questions, maybe we can finish this presentation session. So thank you very much for all presenters in the sessions. And I think I will return to the MC. Ibu Tanti, please.
Okay. We would like to express our sincere gratitude to our moderator, Dr. Ardi Adari Arbain, for giving us very productive session today. And we also extend our highest appreciation to our speaker, Professor Nobuhiro Takahashi, Ms. Sophia Lestari, PhD, Dr. Wendy Harjupa, Mrs. Rahmawati Syahdiza, and Mrs. Anis Purwaningsih for delivering such insightful presentation. And ladies and gentlemen, as we come to the end of this workshop, we would like to invite Dr. Trismidianto, who is presenting Dr. Albertus Sulaiman, the head of the Center for Climate and Atmosphere BRIN, to deliver his closing remarks. To Pak Midi, the time is yours.
Bu Tanti, saya yang gantiin.
Oh, oke. Maaf Bapak, silakan.
Okay, so because our Pak Dr. Albertus and Dr. Midi is very busy right now, so I will give the conclusion and the closing remark of this webinar. So I would like to thank all our distinguished speakers for sharing their insightful and inspiring presentations today. So from this webinar, we can see that the observation of radar and satellites and also other instruments could provide complementary perspectives that are crucial for our understanding to the tropical precipitation systems. And equal collaboration, especially across institutions, in this case is for BRIN and ISEE of Nagoya University. And also I would like to thank all participants for your attention and contributions. So I hope the knowledge shared today will lead to continued collaboration and meaningful scientific advancements. So thank you, and I wish you all productive continuation of the workshop in the near future. So thank you very much for your attention. Yeah, Bu Tanti, it's finished.
Okay. Maybe we can close the Zoom meeting, Pak Ardi.
Yeah, so
Okay. Thank you
yes.
very much
So
thank you very much for the all participants for your active participation today. And we wish you have a very pleasant day ahead, and we look forward to see you again in the next future event. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh.
Thank you very much. Arigatou gozaimashita.
Thank you, Bu Kristanti.
Makasih Bu Tanti.
Sama-sama Pak Ardi, Bu Sofia.
Izin leave.
Izin.
Sampai Ibu.